Now, this is a talk to risk assessment, and I think you are responsible to prove that's efficient and it's safe, a new food. And let me focus on proof on safety today. I have two toy examples. I was involved 10 years ago. The first one is the question, are the known target species in a field trial unchanged compared with BT corn with isogenic varieties? Second example are the nutrition and components in oilseed rapeseeds, again, genetic modified versus isogenic. And a third example I used for calculation later. This is a feeding study on animals. There are completely different aims, but similar statistical methods. Let me classify it. First, we have multiple secondary endpoints. It can be a lot, hundreds. Some are planned, some not. And this makes a problem as a random factor in statistical analysis. It makes it rather complicated, similar to clinical trials. The endpoints are differently scaled. We cannot assume that they are standardized, normally distributed, homogeneous variances. They are not. Our aim is to claim similarity for almost all side effects. It's unrealistic to believe if I have hundreds of side effects that are all equivalent in a statistical term. Similarity can be translated in statistical term equivalence. And if you look in the literature today on equivalence, there's a lot of noise. But important is, even for a single endpoint, that a major problem is a choice of delta. And delta is a threshold which we accept for a side effect. The second problem is the relationship between power, sample size, and this delta. That's a very important thing. And if you look carefully on the trials and studies, sample size are rarely defined by commercial or other aspects. And the question is, which effect size is appropriate for our job? And you can imagine if even problems arise for an individual endpoint, how complicated it becomes for hundreds of endpoints. Of course, the story is much more complex, and the designs include blocks, location, years, random factors. Not today, we can handle this. Let me focus on a simple randomized design, old one against new one, that's all. And one of the basic paradigm behind is that we say we have a long-term acceptance of a conventional food tested by millions of consumers, and we believe this is safe. And the question is, or it's a standard, can we compare the new one to say yes, if it's similar, then we can say it's safe. It's a very important paradigm. If you don't believe on that, good night. And the hundreds of species or hundreds of composition and components will be measured or observed shows you a long vector of endpoints. And I come in the second point on this multiple endpoint problem. Simple-minded people are doing the following job. They say, okay, let's take t-tests, and if all the t-tests are non-significant, great. What's wrong? In the first view is very simple to explain by the sentence, absence of evidence is no evidence of absence. So it's very clear. Why this is doing by the FDA? If you look on toxicology, FDA and OECD is exactly doing this job, but the standardized sample size. If you look on the guidelines, it's written at least 5 animals, and any in the world is taking 5 animals. And this standardization can be recalculated into an equivalence problem. So in fact, they do a proof of hazard, a proof of difference. However, in fact, their claim is safety. That would be a possible way if you are able to have a consensus worldwide, take sample size 10 for all these, for instance, feeding studies. Today, I want to focus on proof of safety. And the common approach is two one-sided tests. This is a common approach today. This is an intersection union test. That means you have two tests, and they have to be simultaneously at the same time significant. A test for a lower bound and a test for the upper bound. However, you need a definition a priori what is acceptable, what is a delta. An alternative is you calculate a 1 minus 2 alpha two-sided confidence interval without definition of a delta. Why 2 alpha? Because you have one confidence interval for the lower side and one for the upper side, and they are together must be in the alternatives, therefore 2 alpha. And this allows you a post hoc definition, what is for you acceptable. So that's a way out. If you look on the literature, there is a serious misuse of this 80% to 125% threshold for AOC of common drugs, so-called bioequivalence defined by the FDA. This is for a particular problem defined by an agency, had nothing to do with all problems. There's many confusion among the users. And in most cases, for multiple endpoints, it's unrealistic to believe we have for hundreds of nutritional components an acceptable threshold. And therefore, it seems to be the only way out to transform our problem of similarity to equivalence, to two-sided equivalence, to estimate the confidence intervals, and later to say the decision makers, is it acceptable in this trial? Okay. However, for calculation power, delta is needed inherently. We have no possibility to estimate power without that. And I will give you an example. Tonight, when I came home, I realized this is wrong. It must be 10%, 2 alpha, but I have already my slide over here. And this is a library power of 2 one-sided t-tests. And I assumed that my ratio test, the test is Sasabushi, it's 40 years ago, the null hypothesis is 100%, and my coefficient of variation for the control, here isogenic variety, should be 25%. Remember this value later, I come back for real data. And then you see here, it should be 10%. I assume doubling in both sides. I assume the null hypothesis at 1, 25%, and then sample size 6. And the power will be 65%. If I change this to an endpoint which is more precise, then of course the power increases substantially. However, if I come back and you want to say, no, doubling is much too uncertain, I want to use the FDA rules, and you see what I'm doing here, then my power is collapsing. So be aware that these 80% to 125% are very strict thresholds for a very particular scenario, nothing else. And this means the equivalence problem without definition of delta using an arbitrary sample size is an insoluble problem, full stop. Don't do it. What we learn from this 80% to 125%, it's a multiplicative model. They use a erasure. Of course, we could use it also for a difference problem, for an additive model. However, the advantage is dimensionless. This gives sense. If you look in the literature, what approach these guys are using, they log transform the data, take the t-test, estimate the confidence interval, make the back transformation, and then they are happy. That could be if and if only the data are really log normal distributed. If not, good night. This is a very biased approach, very biased. Don't do it. And there are alternatives. There are non-parametric alternatives. There are parametric alternatives with variance heterogeneity. There are for risk ratios. There are a lot of. Don't do it as a standard. And the question is it in each case give sense to use two-sided hypothesis, like an equivalence problem? Because remember, if you test one-sided, you save power or sample size. And the answer is, in some cases, the endpoints are directed. It gives no sense to look on an increase of vitamins or a reduction of a known target calorie. Therefore, a one-sided problem may be better, more powerful. It's denoted in literature as known inferiority. This is a nickname for that. Second question, which effect size should be used? And there is a debate in the literature to use unstandardized, for instance, the difference of expected mean or the ratio of expected mean compared with standardized. Was a standardization? One simple kind of standardization is divided by the standard deviation. And this is known as Cohen effect size. Here's an example for a species number. And don't be shocked about this output. This is an effect size, and this is a lower and the upper bound for Cohen's effect size. Are you able to interpret this? I am not. I think this is not really a good way. Another way is to use win probability. This is in the last 5 years. This is an effect size for individual claiming. Let's take, these are my fingers on my hand are subjects. And Meyer is asking, can I beat all these guys here in the isogenic variety? If yes, I count 1, 1, 1, 1, 1. If no, I count 0. And I do it for all individuals. And this gives you an estimate of a win probability. It's really a probability. The null hypothesis is for 50%. And I calculate this data. And here, the probability is between 45% and 69%. It gives you the probability of a future unknown individual, which chance you have to be better than in the other group. I think for individual trials, for instance, for animals and humans, that could be a good idea. And in the meantime, software is available. We wrote, for instance, a package to calculate assuming different distributions. Okay. Question again, confidence intervals or tests. For tests, there are a lot of approaches available. However, you run into the problem, you need a delta. And what these guys are doing to estimate delta, both the EFSA, I was a member of this group until they proposed this approach, and I stopped. And Val and Kang is a new paper in December last year by Pioneer Company. And they say, okay, let's take some isogenic known variety in some environments and then estimate the genotype by variety interaction and the environmental by variety interaction and take it as a surrogate for my delta. This has nothing to do with hazard. You would believe that if the variance is small, you have to use shorter intervals. If the variance is large, you must accept larger ones. Is really hazard a function of variance? I don't think so. The problem is even worse. If you take two-sided interval, many in the literature use symmetrical intervals. Is it really symmetrical? Has it the same impact of hazard if a vitamin is increased or decreased? For sure not. So, summary for single endpoint, we are here in the single endpoint. Delta should not depend on the variance, and it is hard to imagine that you estimate this for multiple endpoints. The solution is just estimate marginal 1 minus 2 alpha intervals for ratio to standard, and then you try to interpret post hoc. Here's a nice example for Repseed data, and you see the coefficient of variation. Do you believe that this endpoint should be higher levels than this endpoint? I don't think so. This is my relevance score, and it should be ordered as well. You can use yours, and you will see variance has nothing to do with hazard exception. Okay, I saw my 5 minutes. Going a little bit to here, and coming to multiple endpoints. What you can do is marginal, estimate marginal ones, each for level alpha. However, you should have a claim that all are simultaneously safe, and we're running into an intersection union test. That means the first endpoint and the second endpoint and the kate endpoint must be safe. And this is an intersection union test. If it's uncorrelated, we have a nested intersection union of intersection union because the equivalence test already is an intersection union test. And what happens is it is a very conservative test if you run into hundreds of endpoints. Don't use it. It's so conservative. If you do it with 2 or 3, maybe possible. If you do it with 100, it's not a good solution. Another solution is to take the correlation into account. We can do that. This is a multivariate distribution, here for 2 endpoints, 2-dimensional, and the problem is how to estimate R. And we have to accept multivariate equivalent if it's not univariate. It's a question if we do that. An alternative is to say, okay, let's ask whether first endpoint or second endpoint or 5 endpoint or 100 endpoint is safe. That's a nested union intersection test by intersection union test. We published this for clinical trial safety data and statistics in medicine. And the comparison between both is surprising. Both approaches are conservative, and the second one allows you a claim of at least 1 endpoint or a collection of some endpoints or even all. Both are conservative, and it is not clear which one should be used in which situation. Okay, let me go to a final example. And this is my example. This is a feeding study performed by the EFSA. All these endpoints are here blinded for some reasons, but what we see, this is 100%. We have some increase, some decrease, and if we would accept doubling, then we can say all these endpoints here in this figure are equivalent. Okay, coming to conclusion, proof of safety is a serious challenge for novel food trials with multiple endpoints. First. Second, neither all these delta i's are available, nor a power approach. Therefore, a global test on safety seems to be unrealistic today. Despite of all problems, don't use the power approach as long as not there is a consensus on the sample sizes. Therefore, what we can do is to estimate marginal two-sided 1 minus 2 alpha intervals. That means for each endpoint independently, maybe adjusted for variance heterogeneity, maybe for non-parametric, what you want, and give them back to the decision makers and say, hey, tell guys, is this acceptable for you? Stepwise approaches for subset are possible. A requirement of certain sample sizes is needed, and definitely not sample size as 4, which I can see commonly in literature for field trials. It's not a good idea. Okay, coming to an end. I apologize for my curious slides, but it's written in Knitter. That means all the data, all the R code is in this document. Therefore, it looks a little bit strange. Thanks.